So today I'm going to continue our lecture with capillary column. Okay, class. Basically, capillary column is developed by Michel Golay in 1957. Basically, he found that the long length of capillary tubing having a thin coating of stationary phase coating on the wall of the narrow inner diameter tube. Okay, basically it's to improve the resolving power compared to the conventional packed column. So this type of column it's known as the wall coated open tubular column. Basically, the high permeability or low resistance to carrier gas flow of capillary column enables a very lengthy column to generate a larger number of theoretical plates. Class, as you all know, as the theoretical plates increase, actually the efficiency of the column also will be good. So now, the advantage of the capillary column is actually by using the capillary column, we can improve the separation, okay, with high resolution and reduce the time of analysis, small sample size requirement, and more sensitivity. Actually, it has higher sensitivity compared to the PEG column. So class, this is the example of the separation, okay, comparison between the PEG and capillary column. So better resolution was obtained for a capillary column because more peaks, if you can observe the figure of the separation by capillary column here. So basically more peaks are separated and small peaks can also be detected. Okay, very sharp narrow band increase peak height and greater detector sensitivity, stability, and signal to noise as well, class. Okay, so the comparison between the packed and capillary column, basically, capillary column provide a separation where the peaks have the narrow bandwidth compared to the packed column, while sharp narrow peak of the trace component have increased the peak height relative to the peak of the component that identical concentration in a packed column chromatography. Packed column chromatogram. So because of the geometry and flow of the gas through the packed bed, so molecules of the same analyte can take a variety of parts through the column, okay, en route to the detector via eddy diffusion. Okay, class. Okay, whereas in the capillary column, all the flow parts have nearly equal length. So basically, due to this, the open geometry of the capillary column causes a lower pressure drops, allowing a longer column to be used. So basically, class, compared to the PEG column and the capillary column, so the route of the analyte to travel through the stationary phase, like in the PEG column, the chances for the eddy diffusion is very high. Whereas in the PEG column, the route that the analyte or the solute takes through the column to the detector will be will be have equal length. Okay, it will have a equal length. Okay, now so packed column contains more stationary phase. Okay, often it's very thickly coated on the inner solid support. Okay, there are locations in the packing matrix where the stationary phase will spread over the adjacent particles as well. This is the packed column. And as for the packed column also, some of the molecules of the same component will encounter thicker region of stationary phase, whereas other molecules have increased the residence time in this thicker poles of phase and will cause band broadening. As for the capillary column basically it contains a very relatively thin film of stationery uniformly coated on the inner wall of the tubing. Therefore, this factor basically responsible for the sharp band definition and the narrow retention time distribution of the molecule of the component during the eluting process from the capillary column. So, example of the how the peaks are being eluted, how the peak travels and being eluted and separated is shown here in this figure. So class, basically the comparison between the wall coated capillary columns with the packed column. So you can see the significant difference in terms of in the length as well as inner diameter. Okay, and the total plates number for the capillary column is even more higher, and the resolving power of capillary column is very high, and the flow rate is for PEG column is quite high, and for capillary column is 0.5 to 15. The thickness, liquid film thickness as well, PEG column quite 10. For the capillary column is between zero point 0.1 to 1 micrometer. So in this case class, so capillary column basically a better column, okay, for the GC separation. In a capillary column materials, for example, the plastic material like nylon, they do had the temperature limitation. As for the metals like aluminium, nickel, copper, stainless steel, and gold, they do have some catalytic activity. So if we see the stainless steel, which is stainless steel is very unfavorable in the analysis of polar compounds in the catalytically sensitive species. So therefore, glass, for example, the borosilicate or soda lime, inert, inexpensive, but they are readily available but lacks of flexibility. Therefore, capillary column, okay, material, which is fused silica, was found to be the good ones, okay, because they do have the flexibility of stainless steels with an inner surface texture of more inert than the glass. So therefore, class, usually, like most of the case, we are using capillary column, which is the fused silica capillary column, okay, for the GC separation. So now class, the structure of different glasses as the capillary column here. Okay, this is the example of soda lime, borosilicate, fused silica, and soda lead. So column activity actually may be attributed to the silanol groups and metal ions on the surface of glass capillary. Metal oxides and boron are considered to be a Lewis acid and serve as the adsorptive sites for electron donor species such as ketone and amines, and as also active sites for species with hydrogen bonding capability, for example, aromatics, okay, and olefins. So the absence of these adsorptive sites in the fused silica is basically responsible for its remarkable inertness and is a direct results of the synthesis of this material. So class, basically, if you compare all these capillary column material, actually fused silica is the most inert one. Okay, so the reason that we have to make sure that our stationary phase is inert so that it don't react, okay, with the analyte, with the solute that we are going to use. Okay, so the analyte that we are going to inject and the analyte that going to elute from the column will be the same. Okay, we are just doing the separation class. So in this case, we want a very inert, okay, stationary phase, but it should be good as well. Okay, okay, now class, this is approximate glass composition. For example, soda lime, fused silica is basically 100% is SiO2 class, okay, compared to other materials. Okay, so this is the picture of fused silica. Basically, class, fused silica exhibits a very high tensile strength, and fused silica also has excellent flexibility due to the thin wall of the capillary. However, the thin wall of capillary is subject to the corrosion on exposure to the atmospheric condition and is extremely fragile. Therefore, the outer cutting is needed, okay, whenever we do the fixing the capillary column into the GC. Okay, we have to cut the column because sometimes class, when we frequently cut the column and insert into the column, into the frequently cut the column and insert into the GC. So sometimes some some interference. We can observe interference. So in that case, we have to bake the column to evaporate all the bake the column means we just run at maximum temperature, so that we assume that all the whatever analyte that trap in the column will evaporate. But frequently, if you bake the column, it will spoil the stationary phase. One second thing, apart from these, what else we can do is we can cut the column, okay, the upper part and the down part, then we can fix it. So probably, something that's stuck at the beginning or the ending, it will we can remove that. So polyamide is also serves as the water barrier, and in most of the cases widely used because of temperature stability. And the color of polyamide seems to vary slightly from one column to another, from one manufacturer to another, but with no effects. Okay, so polyimide coating, this is a fused silica column with polyimide coating, and aluminium for column to be operated above 400 degrees Celsius. For example, crude oil, triglycerides, and so on. Okay, so this is the example of triglyceride separation class. So many peaks are here, okay, but about 1, 2, 3, 4, 5 peaks is belongs to the triglycerides. Okay, now, so how to prepare a fused silica capillary? Basically, deactivation, static coating of the capillary columns, capillary cages, uh, then monitoring the column performance. So pre-treatments of the fused silica. So basically, silanol groups are acidic adsorptive sites. Therefore, pre-treatment of fused silica is needed before stationary phase desorption, depositions. So the purpose of the pre-treatment are basically to cover up or to deactivate the active surface sites and to create a surface more wettable by the stationary phase. So the column activity can be demonstrated in several ways. So the chromatographic peak of a given solute can be completely disappeared or partially disappeared as its size uh, if the size is diminished. So the details of the procedure are depending on the stationary phase to be subsequently coated, but deactivation is basically to produce the column to have a uniform film deposition along the inner wall of the capillary. That is the purpose of that actually, class. Okay, it just to make the sites to be deactive, so that it will be more surface to cover. Okay, for the active sites to cover up or the deactivate active surface site to create a more surface that more wettable by the stationary phase. That is the main purpose. So here, class, chromatograms of the activity mixture of uncoated fused silica and coated fused silica after deactivation with carbowax 20 molar. So we can see the difference in separation, class. Okay, well, figure A shows the, only one peak I can observe. This is probably a solvent peak, class. So I can say only one peak here, whereas here actually about 9 peaks. Okay, we can observe. And of course, we have to do some, further method development or temperature programming so that we can resolve all those peak properly. So now, class, reagent that we use for silanol deactivation is actually this is the way. Okay, silicon hydrate polysiloxane or chlorotrimethylsilane. Okay, basically what we are doing is actually we are just deactivating the silanol groups. Okay, silanol groups. So the functionality of the silanol group will change. So the static coating of the capillary column. Basically, the goal in the coating of capillary column is uniform deposition of the thin film stationary phase ranging from 0.1 to 8 micrometer in thickness on the length inner wall of the length of clean deactivated fused silica tubing. Well, procedure is actually fill the column with the known concentration of the stationary phase. One end of the column is sealed and the other end is attached to the vacuum source. As the solvent evaporates, a uniform film is deposited on the column wall. So this is the static column of the capillary columns. So stationary phase for capillary gas chromatography. So in choosing a stationary phase for a capillary separation, remember, okay, you should know like dissolve like, okay, try to match the functional groups present in the solute under consideration with those with the stationary phase. So when a polar phase, when you want to compare to the non-polar one, it's tend to have a slightly less column efficiency. So and must have a lower maximum temperature limit and will have a shorter lifetime if operated for the prolonged time of period at an elevated temperature. So many liquid phases for a packed column via coating method, okay, purpose were unacceptable for a capillary uh, gas chromatography due to the lack of thermal stability at high temperature and instability of the stationary phase as the thin film at the elevated temperature. So as a prolonged usage, the stationary phase can bleed from the column, especially at the high temperature. So bleed means stationary phase can come out, okay, uh, can come out from the column, especially with high temperature. Therefore, a modern capillary column, it's applied the stationary phase that bond directly to the inner wall of the capillary column. That means class, compared to the packed column, actually capillary column, nowadays the modern capillary column, the stationary phase is actually it's attached directly to the inner wall of the capillary column so that we can prevent the bleeding of the stationary phase. Okay, if you have a column bleeding class, your peak, you will get a very, not stable baseline, and the baseline and the column, actually you can from the chromatogram you can evaluate whether it's a column bleeding or not. Okay, if your column start to bleed class, there is no choice for you, you have to change column. Okay, so immobilization of stationary phase on fused silica capillary column by chemical bonding. Basically, this type of capillary column is coated in the conventional fashion with an OH terminated polysiloxane and then temperature programmed to an elevated temperature, during which time a condensation reaction occurs between the surface silanols residing on the fused-silica surface and those of the face. So it is important to take note that both deactivation and coating will be accomplished in a single step process, and it will result as the SiOSi, which is more thermally stable. Okay, so class, this is the vertically polymerized stationary phase example class after the deactivation process. So another one is the free radical cross-linking. So the overall effects of cross-linking is that the molecular weight of the polymer will increase with the degree of cross-linking, and it will lead to the branches chain until eventually a three-dimensional network, rigid network will be formed. So since the resultant polymer is rigid, little opportunity will exist for the polymer chain to slide past one another. Therefore, it will increase the viscosity of the polymer. The advantage of the cross-linked polymer is it's not dissolved by the solvent compared to the non-cross-linked polymer. And this kind of properties actually it's suitable for the sample with larger volume of solvent. In summary, the dimensional stability, viscosity, and solvent resistance of the polymer are increased as a result of cross-linking, basically. Okay, so the common materials for packing for a stationary phase is polysiloxane. Okay, are most commonly used stationary phase for a pack and capillary column GC because of high solute it diffusities couples with the excellent chemical and thermal stabilities. So basically, it has very incooperative function. I mean, a variety of functional groups that can be incorporated into the structure. Okay, and polysiloxane basically is exhibit a very wide range of polarities. Example 100% dimethyl polysiloxane and about 6, and another one is 6% cyanopropyl phenyl and 94% is diphenyl polysiloxane. So class here, according to the structure here, R groups can be CH3 phenyl and can be anything. X and Y is indicate the percentage of an aggregate in the overall polymeric stationary phase composition. Common materials for stationary phase. This is phenyl methyl, cyanopropyl phenyl. So all these are examples of the materials. So as for the polysiloxanes, additional polysiloxanes of various polarities, they do have been developed, such as polar functionalities of 4-methyl sulfonyl phenyl and 4-hydroxy substitution, polyhydroxy substitution as a result, as well as the medium polarity phases, having methoxy terminated and silanol terminated silanol groups. So this is another one example class. Basically, when a column containing a stationary phase, it can display a greater retention for a solute having a given polar functional groups compared to other solute of different functionality. So while on the less polar stationary phase illusion, order may be reversed or altered by the varying the degrees under the same chromatography condition. So kindly take note on this particular um, statement class about the polarity of the stationary phase. So this is the example of the polyethylene glycol, which is most widely used non-silicon containing stationary phase. Okay, it's for popular because of the unique selectivity and high polarity as a liquid phase. The most common one is the Carbovax 20M and the Superox 4. Okay, so the characteristics is given here and the drawbacks is also given here. Okay, now class, these are the examples of the bonded phase, general use of the phase and the equivalence. Okay, in the market actually we can get all those things. Okay, we can have a list of column lah, for GC chromatography if you want to separate your compounds by using GC chromatography. So these are all the examples. So class, conditioning the column in column care is also and a very important procedure that all of you all have to know. Basically, any chromatography column, new or conditioned or packed or capillary, before we run, we will usually purge with a dry gas for 15 to 30 minutes before we heating to the final elevated temperature, basically to remove the presence of air. Okay, so a column should not be rapidly heated at the elevated temperature, but should be heated slow to moderate temperature by using the temperature programming to the desired temperatures class. So basically, we can't heat it up directly. Basically, the temperature will gradually increase class. Please take note these. It should be gradually increase. Okay, excessively or high conditioning and the temperature, it may reduce the lifetime of the column. Okay, so and apart from that class, we must also use the dry carrier gas or install a moisture trap in the carrier gas line. So most of the people class, they don't install the moisture trap. So what will happen, their carrier gas will be contaminated with the moisture. Okay, so we will have a problem if let's say your carrier gas is it's not dry enough. Okay, so do not inject a aqueous sample on the column chromatography on a column containing a stationary phase. Okay, class, bear this in your mind. As for the HPLC, yes, you can inject your analyte in water, no problem. But GC is very, 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 very sensitive class. Okay, do not inject. Okay, aqueous sample, especially water. Okay, it's not it's intolerant with the water. Okay, should not inject water into GC class. Please take note this. Okay, and do not thermally shock the column by disconnect that while it is hot. We have to wait until the column temperature cool downs. Okay, to the ambient temperature, and we must make sure the packings all the condition of the GC is okay to switch off. Okay, I mean, usually we will wait until there will be some green light in the software. So I mean, the software will shows okay, it's now ready, and then you can close. Okay, you can shut down. So kept the ends of the column for the usually class. What we will do, if let's say like most of the case here in Department of Chemistry, if you want to run the GC, okay, for a coursework student or FYP, usually we will use the department column. For those like PhD master student, they will have their own column. So every time when you run, you have to change the column. Okay, so in a way, if let's say you are using your own column, so after you run, what you can do, you have to cap the ends of the column for the storage to prevent the air or dust particle from entering the column. So, and you can save the box in which the glass column was shipped for the safe storage at the column. So basically, you can use that storage box class, okay, to store your column. So with that, thank you so much, class, for your cooperation.